All right. So we're going to start out the series by looking at some orbital mechanics, because that, to me, sounds like a lot of fun. So the definition, I guess, you can view orbital mechanics as how bodies interact with each other on a gravitational level. We're not going to look at electromagnetic forces or any of the other forces. We're just looking at gravity here. So to give you a better idea of how I mean, let's say that. So we have the Earth. Isn't it lovely? I like it. I live here. And we have ourselves a satellite in orbit around the Earth. That is a very big satellite. Hang on, let me fix that. There we go, much better. So we have the Earth, we have our satellite, and we want to know what the effects on our satellite, our happy little Sputnik, is. And we can look at this and we could say, good enough. Yes, but it is also important to notice that the Earth is not alone in the universe. There's also the moon, and the moon has an effect on our satellite. And we can say, why stop there? Let's take a look at what the sun is doing to our satellite. And if we're looking at the sun and the moon, shouldn't we also, let's take a look at what Venus is doing. Why not? And then, Alpha Centauri exists in the universe too. Let's go ahead and check that out. Then there's the Andromeda galaxy, and there's no end, no effective end to all the things that you can consider. If you can see it, it has an effect on your satellite that we would be considering. So the force on our satellite would be proportional to the mass of our satellite times the mass of the Earth in the direction of the Earth. That's what this whole symbol means. And it gets weaker by the square of the distance to the Earth. Okay, well that's the Earth, but then there's also the moon, because the moon is also affecting our satellite, right? And then there's also Venus and the sun. This can get out of control very quickly. So we don't necessarily want to take into account every force, especially since everything is affecting everything else. So we have our satellite affecting the Earth and the moon, and the Earth and the moon affect each other. And the Earth has an effect on Venus, but so does the moon. The sun's in there too. And oh goodness, this can get out of control because that is just at one instant. This entire equation would be different at the next time step, the next instance, which would really be a time step even smaller than this. But with each force acting on each body, the body in question is going to move by the next time step. And so all of our forces, after we've spent an unreasonably long amount of time calculating all of this, are all going to change in magnitude and direction. So it's not constant. And because it's not constant, it is not easy and not fun to work with. So we really don't want to do that. And the solution is to go back to what we had said earlier and say, hang on, yes, all of these other things exist, but really we're only looking at how the Earth and the satellite are interacting with each other, right? Because the satellite is in orbit around the Earth. It's not in orbit around the Moon and Venus and the Earth and Andromeda. It is just in orbit around the Earth. Okay, so this, being the closest body, is going to have the largest force on our satellite, right? So then we can look at everything else and we can say, well, this is kind of negligible. Andromeda, you're so far away. That's just writing on the page. The stars are so far away. Everything else is just so far away that we can kind of ignore it. These are all negligible, which means that we get to ignore that for now. So really, our force equation, going back to this, is, and I'm going to make it equal to as opposed to proportional to, is equal to the gravitational constant times the mass of our satellite times the mass of the Earth, because again, we only really care about the Earth's impact, in the direction of the Earth, and it is divided by the magnitude of the distance squared. All right, so it is late into the evening and I'm editing this video, and it occurs to me that I did not do a super good job at explaining why that is a minus sign. So, I'll give you a little premonition of what's to come, and brush this slot so I can draw you a diagram. So, start Earth. Just so happens to be our agreed upon origin. And then we have our satellite. That is the best circle I can freehand get. So, satellite. All right. From the origin, we know that the force on our satellite comes largely from the Earth. Satellite's perspective, it comes from the Earth, our origin. The force, however, wants to take our satellite and move it back towards the Earth. Therefore, the force operates in the minus. Let's that down. And break down a little bit. Operates in the minus on Earth's direction. Keep that in mind. Again, here, that is why that is there. All right, I'm going to let you get back to it. There you go. And that is your force equation. And of course, we can call it a day here, right? No, because we have the force equation, sure, but what if we want to know how this is moving around the Earth? What if we want to know how to get it out of the orbit of the Earth and we want to send it to Venus? We want to send it to Venus or something. So there's a lot more that goes into it. We don't just want forces, we want all of the dynamics associated with this orbit. So that's a pretty tall order. There's going to be a lot of videos about that for sure. But let's start with just deriving the acceleration. And, you know, that's pretty easy. And you have your force times, force is equal to mass times acceleration, because Newton wrote it in a book. So if we want the acceleration, fortunately, mass is a scalar, so we can just divide it out. So if I'm going to use dot notation for this. We have our acceleration. So I keep in mind that r is position. R dot is our velocity. R double dot is our acceleration. Then we can just drop our mass term for our satellites. And so we have our acceleration. And that's quite nice. That is the acceleration of our spacecraft. But Newton also pointed out that if the spacecraft is being pulled into the Earth, and the Earth is also being pulled into the spacecraft, right? So really, we should also keep track of the Earth's acceleration. You can say minus g mass of our satellite, the direction of our satellite, divided by how far away it is. And we don't have to stop here. We can take note that this is really just the same as the Earth's direction vector. They're pointing at each other, but the Earth's direction vector is negative. So if we want to get the total acceleration of everything that's happening, the total acceleration, we would take the first one. We're going to take our satellite acceleration, and we are going to subtract the Earth's acceleration, because the Earth is moving in 180 degrees, the opposite direction of our satellite. So I'm going to do this. And I'm going to mess it up immediately here. Let's actually have that be the Earth. And actually, let's make that even better by taking into account that it is the opposite direction of the Earth. There we go. Only mistake I'll ever make in this entire series. And then we can simplify. So that cancels out. So we can have our acceleration, the total acceleration, actually be minus g. That was awful. Let's try that again. G, mass of the Earth plus the mass of our satellite, the direction of the Earth, distance squared. Now, this works, but I really don't want to write all of this because that's a term that's going to come up a lot in future equations. So let's go ahead and make a note to ourselves down here that we're gonna make a definition. So mass of the Earth, mass of the satellite. Yep, my satellite's having a great time, you can tell. And, I'm committed. I'm committing. I'm gonna write in blue. And I'm just gonna have that be one character, mu, so that I only have to write one character instead of all of this. So then our acceleration then becomes minus, already messed it up, minus mu r hat over r squared. And this works as our acceleration, as our total acceleration. Especially since, you know, the mass of the Earth is so very much larger than the mass of our satellite. So we can effectively just say that it is just the mass. We don't even have to take into account the satellite mass, really, because it is so much smaller than the Earth. Now, right before I sign off, I do want to make another note that the direction vector is really just over the magnitude of that same direction vector. So another valid way of writing this that you may see me do from time to time is write it like that. And I'll pretty much just write that for derivation purposes, but these two are equivalent to one another. So I believe that is all I'm going to do. That is not all I'm going to do. Haha. I remembered one more thing, because this isn't the full story. This is just the free fall acceleration, because there's a number of other things that are going on. So I'm gonna use the first definition. Fine. So that's the free fall, right? But then
Yeah, I gift here. That term should be squared. That right there is the only mistake I will ever make.
we also have this term. And this is largely just to keep track of other things, like perturbation forces. So, for example, if we wanted to include like atmospheric drag, because if you're in orbit around the Earth, the atmosphere just kind of goes out forever. It gets much, much less dense the higher you go, but it doesn't strictly go away if you're in orbit. So there is a very small effect from drag, so small that it is a perturbation. It goes into this term. So there's perturbation like drag, there's perturbation like solar. Solar radiation pressure, where the excuse me, sorry, I hit a button there, where the sunlight exerts a pressure on our satellite, and that can affect our orbit. And then there's oblateness. So the Earth isn't a perfect sphere because it is rotating. It is ever so slightly squished. So that can also affect how an orbit looks, how an orbit is. That affects an orbit. And then there are other things. Other things to take into account. Like, I don't know, maybe we're in a high enough orbit that maybe we should start taking into consideration the moon. There's a whole bunch of other reasons to have this term here. And while I'm thinking about it, let's not forget that if you want to change an orbit, so if you want to push your satellite to a different orbit, that would be taken into account in this term as well. So that is our total acceleration for our satellite. So that, I think, is all I'm going to do for this particular video. I look forward to seeing you in the next one.